excited to share some of our past project, current project on how we develop scalable underwater perception solutions, and those are together trying to build like the foundations for better marine autonomy. Before talk about technical details, just a quick introduction on me. I'm currently a third-year PhD student at University of Michigan. I'm serving as a research assistant at the Field Robotics Group and also the UM4 Center for Autonomous Vehicles. I'm interested in multimodal perception, state estimation, and mapping for mobile robots, which include like underwater robots and also autonomous vehicles. So as I mentioned about marine autonomy, so here is a like motivation example on why enabling marine autonomy is important. Here I show like two examples where like underwater unmanned vehicles can help with like environment monitoring and also shipwreck survey. And such solutions have benefits in like safety, cost, efficiency. So the next question become like, is this like hard? This is like a figure from a very famous paper published in Science Robotics about the grand challenges within the next like 10 years. In this like paper, doing like achieving like marine autonomy is like a huge part of it. And so yeah, it's definitely hard. But before talking about how we develop solutions for that, I just want to quickly introduce some basic concept about like autonomy. So usually we do like modular designs for like autonomy solutions, which include like perception, planning, and control. And the group I'm working in is more like interested in like perception. And under the perception, like big umbrella of perception, there are like multiple tasks within that. I listed some of them, but it's definitely not all of them. In the first half of today's talk, I've been talking about how we develop a multimodal state estimation and mapping solution that is also a low-cost solution to facilitate development. And in the second half of today's talk, I'll talk more about how we design a high-fidelity, scalable, and GPU-accelerated underwater simulator to construct high-quality digital twins. And this like simulator will be able to help a lot of tasks, such as listed here. Together, combining these two projects, we hope they will collectively build a solid foundation for enabling marine autonomy. We want to begin with one of the fundamental challenges with like state estimation and mapping for marine robots. So basically, vision is really unreliable as a navigation source in low texture environments. And even when the robots are serving like highly textured regions where the like vision-based localization methods can like track the robot well, robots can still lose tracking when moving over textureless regions. And in underwater environments, such a mixture is like very common and it's like unavoidable. And here I show like an example where like the state-of-the-art SLAM method called OpSLAM3. It can track the robot pretty well when there are like not number of features that it can detect. As you can see, when the number of features like decrease, the trajectory like quickly like explodes. Another example here I show even suffers from like initializing itself into like a stable state to be able to track the robot well. Therefore, we propose a solution called we call Turtle Map. It's aiming for enabling real-time localization and dense mapping. Our contribution includes hardware and system design of a low-cost robot platform. We also develop a Postgraph-based state estimation package to fuse multiple sensors and achieve robust performance on low-texture environments. This framework is based on ROS, so it's compatible with a lot of packages, and it can achieve like real-time dense mapping on a very low-cost embedded computer. So as an overview, two main contributions is our, like we develop a low-cost robot platform, and then also we propose a localization and mapping solution. So I'll talk about our hardware design first. So for underwater perception, when you want to include more sensors, usually it's how to make them waterproofing is a fundamental challenge here. As I said, we have as you might say, like we have a stereo camera, which is not like waterproof, and we also have an embedded computer. Therefore, we design a sensor enclosure to house the stereo camera and also an IMU and also the embedded computer. We have like Ethernet terminals to make it able to like communicate with like the electronics enclosure and the surface and our like topside laptop. So we want to maximize the scalability of the solution. So we choose like low cost solution. In underwater, when we want to like construct a map of the environment, usually we'll be like deciding between sonar versus camera. A typical imaging sonar will be able to also give you like depth measurements of the environment. And here is an example I picked online, which claims that it's a high performance multi-beam image sonar at a game changing price point, but maybe everyone can make a guess, but the actual cost of this sonar is like 9K, which is actually more expensive than the robot platform that we showed, the blue robot platform. So we look at the camera and we find like there's already a lot of like stereo camera options that are able to like construct, like give us like the depths pretty well. This is like a real-time. This is a real-time depth that's constructed from this that mini camera. So we hope to enable the application of this type of sensors underwater, so people can benefit from having a lower cost solution. Yeah, and the price for it is like only like $499, so it's definitely like a much cheaper sensor. But to use this camera underwater, it's important to do a recalibration of it, and it is like a very critical solution because, as you can see, if we use the default calibration due to the different medium of water, the reconstructed the depth from the camera is not reliable at all. We tested the camera, the stereo camera's depth using a artificial rock platform we have in the lab. As you can see, after our underwater recalibration, you'll be able to construct the plan pretty well and construct the overall shape of the rock. But the calibration is not easy underwater. Here I show like how we do this in our like test platform. This was where I collected some data for evaluating this solution. So and accidentally just like get dragged into the pool. But luckily we got pretty good results and calibration parameters from that day, and it works pretty well in our follow-up test. To do calibration, we tested multiple packages available online. We tested like the caliber. We tested like default calibration tool in MaTLab and OpenCV. There's also a lot of our calibration targets that can be used. After a lot of trials, we finally found this combination like works the best for us. So that's all for the hardware part. So now I'll talk more about how we design this software solution. So as you can see, in our localization stack, we use DVL, which is short for Doppler velocity log. It's used to estimate the linear velocity of the robot relative to the sea bottom. We also use an IMU to estimate the angular velocity and acceleration. A barometer is also used to measure the depth of the robot to the surface. And we fuse these three types of sensors in a post graph. So basically a post graph, it has two components, a graph and a vector. The pose is the variable we want to estimate, so it's basically the state of the robot. And we use vectors to connect poses in the graph. So the vectors basically adds like constraints based on the sensor measurements. So we have like DVO, we have MU and parameter connecting in between like vector, connecting in between poses and solve them. And each time when a pose is added to the graph, we launch like graph optimization to estimate the latest state of the robot pose. And in our localization step, it's actually a multimodal odometry within a post graph. The parameter is used for estimating the depth. MU is used for angular velocity acceleration. DVL estimates the linear velocity. We implement this in like very well-known like graph optimization framework called GTSAM. It doesn't have official support for parameter and DVL, so we added our own like, customized factor implementation to that. After we achieve like a robust state estimation, we publish the states using like ROSE TF tool. And as you can see, after we conduct like accurate like underwater recalibration, we will be able to get like very accurate depth point count. We use open source real-time volumetric mapping framework called VoxPlus to construct dense map. We did a real-world experiment to validate the robustness and the performance of the proposed turtle map. Here we conduct like a real-world experiment at the towing tank at University of Iowa because they have a capture system that we can get like ground truth localization to evaluate our framework. It has this like artificial beach, so it's also adding some like difference in the distribution of the like bottom surface, and it's also a good place to evaluate if our framework can construct the map accurately. And this map will be helpful for like amphibious vehicles, surface vehicles to do like tasks such as like mode transition. It has a lot of areas that's a very low texture, and it also have like we also have an on-site wave generator so that we test our systems under the robustness of our proposed solution under environment disturbance. We tested our solution in two logs. The first log we didn't launch the wave, and we drive the robot to survey the tank, trying to get the most coverage of the and construct the map. The second log we launched the wave and test if it's robust against environment disturbance. There's only the like central region has like valid motion capture tracking, but we evaluate the overall. We evaluate our mapping over at a larger scale. As you can see, our proposed solution was able to outperform like a pure DVL odometry or like a common filter based solution to and outperform them by a lot. Here's a qualitative trajectory plot. As you can see, our solution, the turtle map, as shown in red, from starting to the end, aligns with motion capture ground truth trajectory the best. Here's a like live demo showing like running turtle map in real world. This is from the first log where it doesn't have wave. As you can see, it can track the robot pretty stable, and the robot will do like ascending, descending. It will do like turning, and you can see like combining our proposed localization and the accurate depth prediction. They combine together, construct the map of the environment pretty well. In addition to just mapping the bottom surface, we also place the artificial rock you might have seen in previous log. So this also like demonstrates that our solution will be able to also capture like small objects in an environment. So this is a like overall qualitative result we have from the first log. As you can see, at a pretty large scale, our the map region matches pretty well with what we captured with our phone. It's known by the like 3D model that the bottom surface is flat, and you can see like the overall geometry of the constructed map is also like flat. It does also map the artificial beach, so that's also pretty helpful. So for example, the amphibious vehicle will be able to know the distance to the bottom surface to be able to execute like land to sea or sea to land mode transition. The robotic is also mapped pretty well. We have ground truth like 3D like measurements, and those measurements like the size matches pretty well with our ground truth measurements. So Turtle Map as a scalable and robust perception solution is we released our code and the data logs we captured. And it's getting a lot of attention from the community, and we really hope it will inspire future research on enabling more robust data submission and mapping. So that's all for the first half. Hopefully that Turtle Map will be able to like deploy robots in more environments that they are not capable of doing before. But in our second part, we want to address the cost of the high cost of data collection. As you can see here, as you can imagine, if we like conduct like real world experiments to collect data in this type of environment, how resource intensive this will be, and it will also definitely also require like sophisticated hardware and controlled experience setup, and a lot of field work will be involved as well. And we have already seen a lot of like in other fields, there are like scalable and high fidelity simulators. For example, the Isaac lab, which is able to learn like good like policy models from simulation, policy and perception models from simulation, and transfer well into real world. The Isaac lab is part of the like Isaac Sim NVIDIA Omniverse, and also the 3D workflow called like universal scene description. There is some like 3D workflows that's using this open USD framework to achieve like filmmaking rendering quality. So it's definitely like a high fidelity like 3D workflow. But when we look at underwater domain, it can be found like, for example, the NVIDIA Isaac Sim, it doesn't have any support for like underwater sensors, such as like it doesn't have support to model like underwater imagery. It doesn't have support for like acoustic sensors, including like sonars, GVL, lanterns. And some of the state-of-the-art underwater simulators are suffering from, for example, here the Whole Ocean. It suffers from CPU-based like ray capturing algorithm to like render sonar measurement. So as you can see, it's like pretty slow and not like super capable of generating large amounts of synthetic data. Here's like a quick summary on state-of-the-art simulators. Whole Oceans, as I mentioned, it does have support for, it does model like realistic acoustic sensors, but there is no like realistic image formation model inside that. You might also see that like the fidelity of this simulation framework is kind of low. It doesn't have a GPU-based sonar rendering, so it runs like slow when you have to like render sonars, which is a very important sensor for underwater like navigation and scene understanding. Another simulator called UNAV Sim, it leverages Unreal Engine 5. It has pretty high fidelity in modeling like underwater imagery, but it doesn't have any support for acoustic sensors, thus making it hard to like generate like sensor measurement pairs. Therefore, we design a simulator called Ocean Sim, trying to make it a huge step towards a unified high performance simulator. It's based on NVIDIA Isaac Sim, and it's definitely a part of the NVIDIA Omniverse ecosystem and the USD 3D workflow. Some key benefits will include like real-time ray tracing, high fidelity underwater image rendering. We also enable user-friendly 3D workflows powered by the OpenUSD, and we implement sonar rendering algorithms on GPU to leverage like parallel computing. And you also have like native support for ROS, so a lot of existing frameworks can be like seamlessly integrated. Here we show some of the diverse underwater scenes we support in Ocean Sim. This is a towing tank we usually do our data collection in real world. It's at the Marine Hydrodynamics Laboratory at University of Michigan. We collect 3D scans of the environment in air and put it in Ocean Sim. Ocean Sim is also we also have a shipwreck thing that will simulate some of the shipwreck survey tasks. And Ocean Sim is also validated to be able to interact with like online 3D assets properly. And you can definitely like create your own, and just as long as it's format supported by OpenUSD and NVIDIA Omniverse. Here we show something that's not achieved in previous simulation. That's like very efficient scene customization workflow. Here we directly import our the towing tank 3D model into Ocean Sim, and we can customize a lot of stuff. We can put like objects in it. There's a vast amount of available 3D assets in like Isaac Sim and Omniverse. As you can see, we put the rock platform we used previously just in this scene, and we can like flexibly adjust its position, how it interacts with the scene. We can also put other like available 3D assets, so you can collect data for maybe like object detection, sedimentation underwater as well. Here we enable gravity, so that's why you'll see like you fall down. You can definitely make it like float. One benefit of the Isaac Sim is like it's a very easy customization of the overall like 3D environment you want to do simulation. Another benefit is that we can outperform the previous solutions a lot in rendering speed. Here we show like with our GPU based sonar rendering, we can do this. We can generate this sonar image pairs in real world, and you can see like you can achieve pretty high fidelity as long as you have high fidelity like 3D models. And we'll also quantitatively compare against the previous civil art simulators. As I mentioned, the Whole Ocean, it uses oak tree based CPU recasting solution. So it also requires like a cache process as the first time you import a scene. While for like Ocean Sim, it doesn't require to do any like pre-processing of the scene to save cache. So you can like directly customize your scene and then start generating your synthetic data. And it does outperform the Whole Ocean in like frame rate a lot. Another thing I think in previous talks or like presentations, people have talked about how underwater image will look different from in air. And we develop an image formation model that address attenuation and backscattering, and we also provide this user-friendly like graphic user interface, so that you can. I mean, we understand like the users want to simulate different water types, different environments that may have to require to tune the parameters. So we offer like a very easy tool that you can just interact. You can just tune the parameters and directly see the real-time rendering results. So combine all these benefits, OceanSim provides a possibility of efficiently building digital twins. Here is a comparison of a real-world log and what we replicate in OceanSim. It's the same like towing tank 3D model, and we are able to generate realistic images, DVL measurements, sonar measurements from it. And this is played in as a roll spec in using rows, so it also have like support for rows. And we hope OceanSim provides a huge step towards a high fidelity underwater simulator. We will be releasing its beta version hopefully in March 2025. And this is a project website of it. There's like a quick form where you can put your email, so you will get like updates when we release a model, or have like huge updates on features. The preprint of the OceanSim paper will also be available at that time. So a quick conclusion. TurtleMap hopefully could deploy more robots in unexplored environments. It's the first robust data estimation and dense mapping solution in low texture underwater environments. It's also like open source, and we hope OceanSim could help to generate large-scale, high-fidelity and synthetic data set. And it's also powered by GPU, and it's a part of a fast-growing ecosystem and has efficient 3D workflows. And definitely acknowledge all of my collaborators. This is a QR code to the lab page of our group. And I'm happy to take questions.
Thank you. Any questions?
Regarding the old support only 4 frames a month or 5 frames a month?
Yeah, so the question is about if OceanSim supports multiple types of sonars. Yeah, that's a great question. Currently, we support the forward-looking image sonar, and we also support like just like a simplified model, like 1D, like a pin type of sonar. It's our ongoing work of adding support for example, like the side scan sonar, and since it will be open source, so hopefully we'll release that model soon as well. Yeah, but in the first release, it will be imaging sonar and the pin sonar. Yeah. Yeah. So for TurtleMap, so the question about like cost, I guess cost analysis of TurtleMap. So the additional cost would be like building an enclosure for housing the stereo camera and the embedded computer and also the stereo camera, because we assume like most of the underwater vehicles will have or like sort of have access to a DVL. That enclosure took us a lot, cost us a lot, because it's kind of the first prototype of that company. We collaborated with them to build that, but we released like key design details on our website. So we hope like people who have like access to lower cost like manufacturing will be able to like build that in like a much lower cost. That enclosure costs us like close to like $3K US dollars. I mean, in addition to that enclosure, the only cost would be just like the camera, which is $499, and the computer, which is $300. So yeah, it's running on Blue Rock. Something like that. Yeah, we definitely see people getting manufactured enclosure at a much lower price point. So if you have access to that, that'd be great. Yeah.
First one, the huge pool, the rate generator, like, do you have open access to that? Like, is it part of your is it research, or is it some location that you have and then plan and experience?
Yeah, I can answer the first one first. So it's about the test site we tested turtle map. It's a towing tank at the University of Iowa. They are part of that project funded by ONR. So that's why we can use their test site and collect data. But as I mentioned, we release the two data logs with our turtle map. So you will be able to use that for your own, I guess, research need. For example, if you want to add like more, like I guess like visual factors or loop closure into that feel free to use that. It's available here.
And the second question was regarding the ocean side. So like to replicate, let's say, enclosed environment, and you also show the shipwreck, and so like the maps can be like large.
Yeah.
And is it like possible to interact with the environment and dynamically change it?
Yeah, so that's a great question. That's about how, I guess, in Ocean Sim, the simulated robot like interacts with the surrounding environments we put there. So currently, Ocean Sim is a perception-oriented simulator. So that means we don't model like too complex, I guess, dynamics in between objects and environments. Now all the environments are imported as like a rigid body. In our hopefully the next version of a more unified version, we hope to add like fluid dynamics and also add more realistic like dynamics of the robots to hopefully enable like a direct transfer of like maybe like a policy model learned from it. So yeah, so as it stands now, Ocean Sim is a great simulator for generating like data for like perception for like state estimation. Yeah. Yes. Yeah. Anything basically. For example, as long as it's like an OBJ, like or like any like popular model, I think it's supported by the Zephyr. Yeah.
Awesome, thank you. I have also a couple more questions, but let's do that another time just because of time. Thank you again.